I think maybe I will put automatic recording, maybe the moment we start. All right. Okay. So yesterday we started discussing about introduction to NLP and LLMs, where we discuss about general concepts such as why NLP is hard and also the different kind of tasks you can do. So this is our repository. If you don't have this link, you should be able to see that in the chat we already have in our Discord. Um, Again, we have the link for the YouTube link where you can see the recording. And these are some of the suggested readings we have for the lecture one. So you can see we have three papers, which if you read, it will give you the general understanding of, NLP and also some of the research field. For example, in House NLP, this paper, if you are interested in Hausa natural language processing, when you read this paper, you see some challenges and future directions. And this paper you give you the all the Africa NLP. If you read this paper, you will get a sense of a review for what is missing in Africa NLP, and this is global. So we started from the global, come to Africa, and come to Hausa. So this kind of give you an idea of all the progress we have in our NLP. I would also like to remind us about the course we already talked about, which is Google DeepMind AI Research Foundation. So for anybody, for you as part of this cohort to receive, a certificate from our fellowship, you must finish all these courses. The first one is on build your small language model. Google DeepMind train a small language model. So all these five, 1, 2, 3, 4, 5. If you see this one, which we already discussed, it has some lessons. If you look at it, these are the lessons. And at the end of the day, you will have the course badge. So course badge is when you finish this course, you will have this course badge. So this is something that you can do at the comfort of your availability. Um, and then by the end we finish this, you already finished this one. You can see them, they are not that terribly 6 hours, 1 hours, 4 hours, something like that. So while we are working through these classes, you still working in parallel, with this. Yeah, so this is just reminder. I hope at the end of this you will have a very solid understanding of NLP. Okay. Now, going to the section today, what we're going to discuss is how large language models started. So basically, now you see we have been seeing ChatGPT and the like, but how these started? They have been large language models started since the early of many couple of decades since 1950 also. They have been there, but the language model started. There are a lot of limitations. For example, the compute limitations. We didn't have huge amount of GPUs to train model. Data. We didn't have a lot amount of data. In fact, the early days of language modeling were statistical in nature. You do some statistical analysis, rather than today where we are using just deep learning, where we just give the models data and it learns data, it learns, pattern automatically. So what we'll be seeing today is the evolution, how language modeling started, and some historical fact. Of course, we have some, the references as well. These are the references you need to read. Okay, let me dive into the class for today. So this is it. How language modeling started. Can you see my screen?
Yes, sir.
Okay, so how language modeling started, that's what we say the n-gram and and statistical error. So what you need to do to understand more about this is the chapter 3 of the book we already gave a reference, which is the book we already discussed. This book, if you go to no, okay. This book, Speech and Natural Language Processing. This book. Mhm. Okay. Maybe something wrong with the website. Okay, maybe the Stanford website is down. But you know the book. So I'm talking about the chapter three of this book. So if you read it, you'll learn more. Basically, that's what we'll be discussing today. And yeah, so you see, nowadays we have different kind of language models, right? We have GPT-3 since 2019, T5, Bloom, you can see them, Cogen, Alpaca, Flan, whatsoever. You can see them a lot, right? Llama, GPT-4, now we have Bar, but all these things now you can see from the year, you can see from 2019 here, it's all these they are getting, getting names. But the language modeling started early than 2019, even before the Transformer paper. So how does this actually started? So what do we mean by language models? Um, you know, the language models we have seen, for example, large language models such as Gemini, GPT, and all these ones, they did not started just out of the progress we have now. They evolved from what we call simple statistical foundations. So they evolved from the idea of what we call n-gram models. So n-gram models, they are basically the models that started using probabilities, and that's what they pave a way for this today's LLM. So the Ngram, these are the very first language model. So when we say language model, that is, a way to understand language. That is language modeling. So that is it. So this we have the first one we have is what we call Ngram language models. So what is Ngram language model? Anybody can help us in the chat. Ngram? What is Ngram language model? Ngram language model. Ngram language model. Anybody knows what is Ngram? Ngram. Number of words or token. So what do we mean by when we say Ngram language model? Okay, so let's go dive in. So we'll come to that. So we know nowadays these language models, what they are doing basically is prediction, right? They predict given something to give that one. But we know prediction is really difficult, for the future, especially for people of faith. We know that you cannot predict exactly what will happen, for example, tomorrow or something like that. But for text, when I say M South Africa is located in, I can say that where it is located. I can predict, right? And also when I said Kano State is located in which country, I can basically predict to say it's located in, Nigeria. So you can see you can predict next war, right? It's very difficult to predict what will happen tomorrow. Because tomorrow is future, but you can't predict what given a sentence because of the contextual and context of those texts, you can predict what is next. So here we can see you can have this. So language model. So what language model does basically is predict the next word. That's basically when you hear we are saying large language models, we basically mean something that predict next words. So, for example, ChatGPT and all this stuff, what they are basically doing, they are predicting next word. When you ask ChatGPT to write a letter for you or it answers something, basically behind the scene, it is doing predicting next word, next word, next word, and now come up with a fully full blown text written. So at behind the scene, what this models are doing. They are predicting next one, next one, to make sure that each word that is predicted is coherent, makes sense in the text. That is what we mean by language modeling. Language modeling is a task of predicting next word. So, so you can see this is basically what language model is. It's a system that predicts the next word or sequence of words in a sentence. That's basically what it is. How does it does that? It basically assigns probabilities of the next word. It is not rightly predicting only one word in a way that, okay, I'm going to the restaurant to this. No, it will give probability from sequence of word. For example, here you can see we have market, we have store, we have mosque, right? So if, for example, if it is like you're a Muslim and somewhere you say, I finished my ablution and I'm going to the dash dash. Now you see that because you finish your ablution and you're going to dash dash. Now, if you give this, we have market, store, mosque, then market may get like zero point 0.3 probability, this may get 0.2, and mosque may get 0.9. So because the probabilities of words that comes mosque is higher, then what will happen here is mosque. So this is basically what language model is doing, is basically selecting probabilities, possible probability and assign to text. So this is next word. But what about assign a probability to an entire sentence? How likely, or fluent sentence is? So a language model is machine learning models that learn pattern in text so it can produce probability distribution over possible next words. So this is basically what we mean by language model. We obviously know that already that NLP is a field of where we have machine learning, but machine learning you can see is general. But the general idea is that it's somehow a field that deal with text. So this is basically what is language model. Any question? If you have question, you can put in the chat. Yep. Okay. Now, why predict the next word? Um, to predict the next word, we basically need to carry out a lot of stuff. So, for example, one key things to do that is for machine translation, for translation, summarization, speech recognition. All these ones, help also do that. If we are doing grammatical correction for text, for grammar, we can know that the word that comes next, for example, I he know the boy. He knows the boy. If I know the structure here, he know. Somebody say, okay, the because I use he, the next word will be knows, not know, right? So you can see that if we use language model to predict the word after he, no will not come, only knows will come, right? So you can see it will help us to learn grammar, to correct grammar. All these things you are doing to correct grammar, for example, given a chat GPT to correct your grammar, it is predicting what probably can comes next so that it can correct your grammar. What orders you can see what order what naturally follow each other, meaning understand the context. So all these ones, they are important in predicting the next word. Um, Here, for example, there are two midterms. There are two midterms every. There are two midterms. So you can see here this there is not correct. We can do spell checking or grammar. Check this one. Everything has improved. Everything has improved. You can see this. So you can see all this one. Predicting the next word can make sure that the next word you have actually follow the grammar. So as I said, this one here, language models actually does not actually just predict the next word. No, 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 no. A language model does not predict as just one word. What it basically it predict likely probability, right? The likelihood for what will be the next word. Yeah, so that's what it basically does. It predict what is gonna be the next word. Um, so which sentence below sound natural? You can see here we have all of a sudden I noticed three guys standing on the sidewalk or on guys all of so you can see a language model will assign higher probability to the first sentence because it follows natural word order and meaning. So this is basically what language models is. Whenever you hear about the word language model, what language model is basically something that assign probability to the next words. Yeah. Okay. And language models are everywhere. So, for example, machine Google Translate, is using language model as you can see, because the trend Mumbai is today to translate this one to this. All this, for example, ChatGPT, you can see Grammarly here. We can see ChatGPT. All these one, they are, application of language models. Now we have language models, as we say, they are everywhere. But now remember what we are talking about today. We say large language models, right? Large language model. Now we attach another word before called large before language models. So today, language models we have, they are large language models. Why they are large? Because they are trained with massive amount of data, such as all this one, for example. You can see them GPT, Gemini, Claude. All these one are large language models. Previously, we have language model. Language model, even statistical language model that we see, such as Ngram, they are language models because they predict next word, but they are not large language models. So that means even in those days we have language model, but they are not large. Today's language models are large. Why? Because they are trained on massive amount of data. They are trained, with a high number of GPU and many stuff. They are called large language model. So now the language models, you can see some of them they are open, some of them they are closed. What we mean by this is that some language models they are open, meaning that their code, their data, everything is open. That is, you can be able to see them. You continue to return on them. Some of them they are closed. They are closed because we are using them for for business, so such as Gemini, Cloud, GPT. All these ones are closed. You cannot basically see their code, continue training them. But such as Llama, this is open source. So, for example, we have Llama 4, so we can take Llama 4 and continue training it, for example, on a Hausa language, in massive amount of Hausa data, so that when we train it on massive amount of Hausa data, Llama 4 will now understand more Hausa, will have more performance on Hausa. This process, taking of existing language model, open language model, and continue training it on another data is what we call continual pre-training. Continual pre-training. We have what we call language continual pre-training, non language adaptive pre-training, continual pre-training, LAPT, language adaptive continual pre-training, meaning you take an existing language model and now continue training it with more data for a particular language. That is called language adaptive continual pre-training. We have for example, if you take Llama 4, it was trained on multiple language, maybe 100 language, English and whatsoever, maybe with Hausa, but the Hausa data was trained on is very small, and its performance on Hausa may be very limited. Now, for you as a student, maybe you are interested in Hausa, now you can create massive amount of data for Hausa. You can scan books, you can start, many things. You can create very huge amount of data for Hausa. Now, when you create that data, you now take Llama and now continue training on it. Then you can, adapt it that you can have Hausa Llama. So when you say Hausa Llama, it means it is original llama that was taken and continue training it on Hausa data, that is Hausa llama. So these are some of the projects one may do. You can even take Gemma and continue or Mysterial and continue training on Hausa data. So this is what we call language adaptive fine tuning. We also have what we call TAFT, task adaptive fine tuning, which is basically take some language data and continue on data. So just to this one that I've been talking about, we have a paper called Afro SLR, Afro SLMR, social. So this is one of our paper, called Afro SLMR. So we follow this idea of tapped and dark. What we take a language model called Afro SLMR, which is basically a language model created for African language. It was created on many, many, tags, many languages. You can see the languages a lot, and it was good. So what we basically does is that we take this Afro SLM language model, we created social media data only, like Twitter, Facebook. We created for African languages. Now we continue training this language model. So this language model, you can see it, Afro SLMR large is language model. You can see it in Hugging Face here. We take it and continue training it on a data set we got from social media. We get tweet data from for Hausa, Yoruba, Igbo, and now we said, okay, now Afro SLMR will be good on maybe good on any data, but it may not be good on social media data. So when we continue training it on social media data, it turns out our language model has better performance than Afro SLM on social media text only on social media. So this is, you can see we created a data set called Afro Social, and then we do that. So this is something that you may be interested also to create. Maybe you can say you create your house Lama or house or something by continue training on many data. So a language model is fundamentally statistical in nature. What we mean by this is that a language model, no matter what we have, in fact, whether even the BART or GPT, they are statistical in nature. They learn pattern from large amount of corpora. So that's what they do. They learn, learn patterns from huge amount of corpus. Yeah. So for example, one of you may say, okay, because at the end of this class, we're gonna have like project where everyone will take what he can do. For example, one will say, okay, I'm gonna create Hausa Llama, continue training Llama on my data or data. So some of that. So, what is language modeling? For more formally, we can say formally we can say the goal for language model is compute the probability of sentences or sequence of sentences of a word. So, given particular word, we can given this one 1, 2, 3. You can see probability of given word up to n. The tags for that is this is probability. Given this or this, a language model compute the probability of these, either of these, probability of word or probability of word given previous word, given the next word. So this is previous word. So probability of n given the probabilities of the previous word. So this is basically, you can see it here, probability of, word 5 given all the previous probability W1, W2, and this. So this is basically what is language models mathematically. Yeah. Okay, any question?
Hello, can you
Okay,
hear me?
yes, yes.
Okay. My question is that is there any numbers of weight that is required before it can be able to predict the next one? For instance, can it be able to predict with two words? Can it be able to predict the next one when you two words?
Cool. Yeah. So that's a great question. That's where we are coming. We have what we call n-gram language models. So n-gram, when we have bigram, it predict two word. We have trigram. So this is where we have that will start language model in NLP from statistical. So we'll come to this, but let's do that. To answer your question, yes, you can have a language model that predict only one word. You can have a language model that predict two or three words or four. And that's why we have bigram, trigram, and something like that. That's what we'll see next. Just give us like 3 minutes. We are coming to that. Okay, so how probability language model work? I have already said, what it does is that, here we have heavy rainfall, big rainfall, right? So heavy rainfall, you can see has highest probability with big rainfall. The festival of light, the festival of lamps. So you can see all this one. So language model actually what it does, there are even close word, big rainfall, but the one with the matching, that has highest probability will now be taken. That's what is the they assign higher probability to sentence that follow common patterns seen in the training data because you may see more heavy rainfall. If you have large amount of data, you see heavy rainfall, not big rainfall. You will not see this. This is unnatural. So the probability of this one will be very, very slow, but the probability of heavy rainfall will be, higher. For example, you can see family gatherings, you can see family meetings. So this one may be more common, and so therefore you see this. So this is basically how these language models work. So language model in NLP for us, statistical to large language models. So now the next thing is we're gonna see the evolution. The language model started the era from statistical language models to large language models. So how the statistical language models? The first 10 categories of language model we have statistical language models, we have neural language models, we have transformer-based language model, we have large language model, we have multilingual and low resource language models. So these are some categories of language model. And the first one we are going to see is statistical language model, large language model. So what is statistical language model? So the statistical language model, which we call Ngram, yes, Ngram. So you can see here where I say we have what we call Ngram. So model predict the probability of end word based on the previous word. So this is a question engineer you ask, a probability of end word. So it can predict like one word which is unigram. It can predict bigram which is two word. It can predict trigram which is three word. It depends. So it basically count frequencies and estimate of that. So this is what we call statistical language models. It predict the number of word you want and you assign those words from the beginning. We have what we call neural language model. So after the statistical language model, which is Ngram, which is the very basic language model, we now move from statistical language to what we call neural language model. This is when we move from statistical, where we move to deep learning. We have, such as, feed-forward network. We have LSTM, we have RNN, and this is actually before pre-transformer. Before we start talking about transformers. So this is what we call neural language model, because we are doing deep learning here, that we call neural language model, because they learn pattern from, continuous representation rather than, from, Ngram stuff. Then we move to transformer-based language models. This is when the paper was introduced. Attention is all you need from Google. So here we have BART, Robata, T5, all this one, we call them transformer. Why? Because this language model, they are based on transformer architecture. And this where we call them neural language model. They are not based on transformer, but they are based on, neural networks, right? Because LSTM, feedback, they are based on neural network. You remember neural network in your deep learning class? Sorry for those of you that you are not here when we discuss in our deep learning session, deep learning class, we talk about neural networks, where we said in deep learning we have neural network, all these neurons so that's why these are called neural language models. And this one they are called transformer-based language model. What about this one? This one, they are transformer-based language models, but not a different architecture. They are transformer, but they are very large transformer models. That's why we call large language models. That's why we got LLMs, large language models. These are based on transformer, but they are very large, right? So you can see such as GPT, Llama, Gemini, all these ones, they are large language model. So here you can see we said LLMs are subset of transformer models. Here we say transformer based model. So LLM here, they are based on transformer method. They are not separate kind of large language model, but they are subset of transformer based model, but they are, they are very large. Multilingual and low resource language models. So here is also another category that I give, multilingual low resource language models. Why they are multilingual? So instead for you to create a language model only for English, for example, such as, BART in the beginning, such a transformer-based language model. You can see this BART is language model, but it is not multilingual. It is based on maybe only on English, but now we have multilingual. When we say multilingual, it means it's a language model with multiple language. For example, MBAT is, you can see from BAT we have M. M means multilingual, meaning like, it's not the original BAT. So it's multilingual, it means it is trained on multiple languages. So all this one are multilingual language model. A low resource language model, for example, this is AfriBata, is low resource language model on African language, right? So these are focused language model. Yeah, so now these are basically some of the categories of language models we're going to discuss. But in today's class, we're going to see details about statistical language model. Any question?
Good afternoon, sir.
Yes.
So I have this confusion. I always try to understand the concept of maybe having 1 billion, 2 billion parameters when we are talking about large language models. So I don't know maybe how to conceptualize the concept to understand what does 1 billion or 2 billion parameters means.
Mm-hmm. Right. So this is something that we'll discuss in the class, because we're gonna see the architecture of transformer. That's when we see, the architecture. We'll see if we say this language model is 2 billion parameters or whatsoever billion parameters. We'll see that. So this will discuss this in more details when we comes to the. So let me just show you some stuff. So here you can see here we have what we call this is what we have. But when we come to this here, for example, attention and introduction to transformer, you can see them. This is the lecture. So here in this one, you will discuss more about because we are going to design transformer based language model. Ourselves, you're going to train. You're going to fine tune. So when you are training the language model, you need to specify how many parameters you're going to use. So this is something we come to discuss detail when we there. So yeah. So I don't want to jump into that to just make a distraction. But when we finish this one, maybe I can talk about that a bit. All right.
Hello.
So
hello.
Yes, another
question. I have a
question.
Yes. So my question is basically based on this statistical language model.
Yep.
I don't know it will be discussed later.
Mm-hmm.
Assuming a model was trained with 30,000 words, maybe like that was like the model was trained with 30,000 words, and during the prediction of the next words, is the model going to give probability to all those 30 words, or it will select some specific words that are relevant to the next word that are relevant to the previous words and give probabilities to to those words only?
Yeah, so that's a good question as well. So his question is that for example, we train a statistical language models with 30 words, maybe 300,000 words, and we basically want to do, as we say, we do assign probabilities to each word, right? So his question is that is the language models going to assign the probability to all those 300,000 words, or are we going to select some subset of words that we are going to assign those probabilities? That's his question. To answer your question, we have this answer in a couple of slides. You see that. So before we finish your answer, your question, just to not to divert, we'll come back to that, and you see. So let's just see this. So this is the statistical language model, probability language model we're gonna see. So what is happening is that the goal, which I already explained, given n word, look at it, calculate the probability of send the goal, calculate the probability of sentence, also you consider n word, right? So if you have n words, recently what you asked, you have n word, like 100,000 or 10,000 words, then we have word one up to 100,000. Now the task for probabilistic or statistical language model is to calculate the probability for each word. Given previous word, what will be the next word? Given previous word, what will be the next one? So all those words at the next word, they will have probability assigned to them. So a model that calculates either of these is what's a language model. So either of these, no matter how the words are, even if you have whatsoever word, we assign probabilities to them to do this. So this is, as I told you here, we have n. N, when we say n, it means no matter how the words are, they are just n. You can do whatever you want. So for us to do this, to calculate this, what is this probability? Can somebody remember the chair rule from the university? How can we calculate this probability? How can we calculate this probability from error from university? If you remember our statistics or whatsoever, probability of this, how can we calculate this one?
Which one, Professor?
This probability of this given these words, given this probability of this given this. So if you go back to conditional probability of B given A, we have this. This is a formula for conditional probability, if you remember. And this can be rewritten as this because this is, probability of A, B here. And then we can have probability of A B given B and then probability of B. So here you can see because we say probability of this is probability of A given B, probability of B. Then if we have more variables here, probability A, B, C, D, this can be written in this format. So which basically extend this to what we call a chain rule in statistics. So this is probability. Now we are not going to discuss this more detail, but if you remember your probability, the chain rule in probability in your statistics class say that if you have probability of this, now is probability of Px1, then given probability of x1 given x2, probability of x3 given x1, x2, up to this. This is a general chain rule from conditional probability. Do you remember this, or we need to discuss more about? Do you remember this in your statistics? Right.
Yes, sir.
Yeah. So even if yeah. So Falalu is writing something Bayesian theorem. Is also part of what you can revise in your statistic class. Now let's look at an example. Okay, Amin Hamza.
Okay, Professor, if I get the point, that means the core differences between large language models and the statistical model, which is SLMs, the SLM use statistical methods to predict the next words, while the large language model are transformer-based.
Yeah. That's right. So statistical language models is using probability, even though even the transformer based, they are using probability, but the statistical language model, they are very classical. I mean, when I say classical, they are very traditional. They are not learning from massive amount of data, but the large language model, they are doing also the same thing, but they are learning from huge amount of data. And they are transformer based, they are using different algorithms, right? So let me give you an example here. Suppose we want to model the probability of a sentence. The cat sat on the mat. So you can see this is the probability of this sentence, right? So based on this formula, this is, we say we probability of X here. So here we say you can see probability of D, then you have probability because of D given cat, then probability of sat, given the cat, all this one. And also I love machine learning. So this is how it works. How you generate this stuff, and you can see, that all these words you can see here, all these ones here, we calculate the probability here. Probability of I, you can see that's the first one. Probability of love, that is the second one. Probability of machine, probability of learning, and giving the previous word. So you can see that when you have n number of words, so you need to calculate all the probabilities may come and this. So this is basically, I will show you an example of this, right in a bit right now. I'll show you an example for that. Now, but how do we calculate these probabilities? Now, here we just show you how this, but how do we calculate this? This is basically statistic. We use what we call maximum likelihood estimate. Estimate the probability by counting co-occurrence and training data. So if, for example, I want to calculate this probability, probability of this, can you see that? Or probability of cat given the probability of sat given the cat. How can I calculate this probability? So this is how you need to count the number that this occur given this, and then probability of this is equal to probability of this given this, and then divided by probability of this one, right? Can you see that? This is a formula. This is probability formula. Let's see an example. Let's assume we have a training corpus with 3 sentences. I'm Sam. Can you see this? Sam, I do not like green eggs and hams. How many sentences do we have here? 3 sentences, right? We have 3 sentences. We have 3 sentences, right? I am Sam. Sam, I do not like green eggs and ham. How can we compute language model probabilities for this one? Now, so how many words do we have? We have this word. Can you see them? Now, who can help us to compute the language model? We have 3 sentences, right? And we want to compute the probabilities of, this. So let's see this. The first one, we use this X. Can you see the XX to denote, the beginning and end of a sentence? Sometimes in NLP, we use some kind of, stuff to show that this is the beginning of sentence, this is end. So let's assume here the beginning of sentence, this is the, end of sentence. So the step 1, what you need to do is count all occurrences, all occurrences of, that's what you need, all occurrences, right? So here we can see that the first one is I, right? So probability of I given S. How many I do we have on S occur previously? How many I do we have S occur previously? In how many sentences? Who can tell us?
Just 2 times. S occur like I come before, like after S 2 times.
Okay.
In sentence 1 and sentence 3, I think.
Okay, so here you can see count the probability of this, the previous one. So here you can see we have WI minus 1 WI. So for example, here we have this and probability of this, right? And remember, for us to calculate the probability, we divide by probability of count how many this I comes. So how many I do we have?
3.
So you can see I, how many here it comes? You can see we have I and we have S
1.
comes. That is 1, right? So why the second one?
In the last sentence, I do not like green eggs and ham.
This one, right? So how many count do we have now? In this case,
2 counts.
2 count. That is this. But what about this one, the total of this?
3 counts.
Where and where?
The first one, that is I am Sam. Then
Okay.
the second one, Sam I am.
And what?
The I after Sam, and the last one,
Right.
I do not like green eggs.
So you can see we can see the probability of I given S is 0 for this, right? Now the next one is we can take the probability of S given Sam. How many do we have here?
We have 2 Sam and 1 Sam that came after S.
Right. So this is basically the first thing we need to do. All this one. This is just counting occurrence, counting occurrence, how many, it does. So if we look at this one, this is, the sentence we have, and you look at this one, all the probabilities, that we have. So if you look at this one, I take all this is just an example, right? This is just an example, but you can take each of these one, this come before this one, and these are the possible, combination you can have. So you can see that why this probability, they account from real text, our training corpora, because this is our real training corpora. For example, these are only training corpora you have. These are the only sentences you have. And high probability, this bigram appear frequently. Now, if you look at this one, which bigram appear frequently, which bigram here has highest probability here in our corpora? Which one has higher probability? because this we have only 3 sentences. If you look at this one here, for example, we have eggs and green, right? Green comes, given eggs, you can see that. So you can see we have only 1% is probability is 1 exactly it comes. But what about this one? You can see here we have only 0.33, and you can see have this one. So low probability the sequence is uncommon. This is just an example because we have only 3 sentences. Zero probability the sequence never appear in training text. That is what we mean by zero probabilities. But this is just an example to show you how statistical language model, given any sentence, it can predict the next word. This is just an example. If you want to create a new sentence, because this is your corpora and you create all this probability. Now, if I said, okay, I have a word, given a new word like, green, given a new word green, what can we predict at the next word now? What can we predict at the next word? Given the word green, what can we predict the next word?
X.
What can we predict the next word?
X.
X, right? And because there is probability is what? 1 is 1. So these are some of the example how these, so here we can see each probability answer the question. Given the previous word, how likely is the next word? So we can see this is what I already explained, what it does. So this is basically, the probability statistical language model, and this is how they are. Any question before we continue? Basically, this is statistics. It shows you how you can do that. Any question? So now we have seen, how we can predict the next word. Given a word and previous word, we can see how the next word is. But what about, for sentences? For example, what is the probability of begun given these sentences? If you look at this one here, what we do is we only find for, bigram for the next word, right? Only one word, which is easy to calculate here. But when you have sentence, it's really difficult to find out the probability of begun given all these sentences, all this word comes together. Given this word sentences comes together, the probability is really low. It is easy to find the probability of previous only single one word, right? So for that, enough data is not available to get an accurate estimate of the above, because what is the count of the monsoon season has begun, given this total word. So the solution is what we call markup assumption. Markup assumptions. So this is the solution that we're going to look at that give us what we call unigram, bigram, and n-gram. So unigram, we call them zero order markup chain. Bigram, we call them first order markup model, and n-gram, we call them end order. Just to let you know, this session is basically introducing us to the basic idea of language model. This nobody do this nowadays, but it's good to get the foundation. What I mean by nobody is that when you are doing research, you may not go back now to do statistical language model. So we are building the idea on why do we need them. So let's look at what they mean. What is unigram language model? So a unigram assumes that each word is independent of previous word, and it does not rely on any history. Yeah. So this is what we mean by unigram language model. That is, if you want to calculate the probability of this, the cat has sat on the mat. Given the probability of this, you need to calculate the probability of each word. Probability of the, probability of cat, probability of sat. That is the model. A unigram assumes that each word is independent of the previous word. So it does not rely on any hints. So there is no dependency. That is what we call unigram language model. What is bigram assumption? So in bigram, the probability of each word depends on the previous word, because we, of course, unigram is not a good language model, because language is something that has context for you to predict the next word, there is some relation between the previous word. So unigram does not have that relationship. What a bigram? Bigrams allow that, the probability of next word, given what it depend on the previous word. So for example here, given this one, so probability of this here we said we give, because it's the first word we can give two, starting two, but given this one, given probability of cat, the given cat, probability of the given cat, right? Probability of this again, probability of what? Sat given cat. Probability of cat given sat at the beginning. So you can see that if we are looking for probability of this sat, we look at what is behind. So this is what we call bigram. So bigram, look at the bigram. Somebody will hear when we say bigram, it means it depends on two previous words. No. So when we say bigram, it means it depends on one. That is, we have n minus one. We use this idea. When we say bigram, so it depends on n minus one. Bi means 2 minus 1. That is, it depends on one word. If we look at the unigram language model, unigram, it means unigram 1, which is uni, 1 minus 1, which is 0. So it does not depend on any word. That is what we mean by this. So you can see unigram is called zero order. Zero order, because it does not depend. Unigram, we say, because uni is 1, 1 minus 1, you can see 0. What about bigram? Bigram means 2, means n minus 1, 2 minus 1, which is first order, you can see that. So when we have n-gram, we can generalize. When we have n-gram, it's mean if it is 10 gram, we have 10 minus 1, which is, you can see, we have a 9th order. So this is basically what we mean by that. So you can see this is the general idea of n-gram assumption. Each word depends only on the previous word. That is bigram. Trigram, each word depends only on the previous two words. That is trigram, which is second order Markov chain. And the general n-gram model, which is case order, is depend on this. So this is basically the idea of what we call bigram and n-gram and whatsoever language models. Any question? So this is basically an n-gram consider only the preceding n minus 1 word. So relation between Markov chain and language model. An n-gram language model is equal to n minus 1 order Markov model. N minus 1 order Markov models. Any question? Okay, let's quickly go again to see some example. So n-gram can be extended to many, 4 gram, 50 gram, as you can see, it can be extended to many other stuff here. However, simply increasing n does not fully capture the complexity of natural language. When we increase the n, for example, even if you have 5, 6, 8, 9, 10 gram, we cannot be able to capture the complexity of language model, because language is very complex. So n-gram model is not a very good language modeling approach, because one of the key problem of n-gram language model is that long-term dependencies are problematic. Long-term dependencies are problematic. The idea of this n-gram language model is that if we have bigram, it can only understand the 2 previous words. If we have 4 gram, it can only understand 4 previous words. 4 previous words, take the context. But let me give you an example where we see the language model that use n-gram has issue. For example, the computer which I had just put to the machine room on the 5th floor crashed. Now, you can see this crash, there is a relationship between computer and crash, right? There is a relationship between computer and crash. But between computer and crash, how many words do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? Now, because we have 13 words, when you have n-gram model with 3 or 4 n-gram or 5 n-gram, there will be no relationship between computer and crash. So when you have the computer, which I had just put into the machine room on the 5th floor, you put dash dash to predict. It cannot predict crashed when you are using bigram, trigram, or whatsoever, because there is limitation, there is huge distance here. So the subject computer must be connected to the BAP crash, but many words intervene far beyond the reach of typical n-gram windows, because the n-gram windows typically they sound like bigram, 3 gram, 4 gram. So if you have the windows is very small, therefore your language model will not be able to connect between this and this, which is a very huge issue. So this is one of the problem of n-gram language model. Just put it in your mind. One of the problem n-gram language model are stopped is long distance dependency. Long distance, so they cannot take care of long distance, right? Let's look at this one. An example: unigram. The cat sat this bigram. The cat sat on the mat near this neural language model. This is an example of n-gram language model. So the cat sat on the mat. This is what the unigram language model was able to predict. Bigram and trigram were able to predict this, but neural language model predict this one. The cat sat on the mat near the warm place for subtly at the evening. So you can see this is a very good sentence, and you can see the fluency. The unigram language model, which is zero order, each word is independent, right? Poor, random word, no structure. The cat sat on sat mat D. You can see this is not a very, even the word order, because the unigram does not take care of the previous word. There is no relationship between any word in that. So the unigram language model just predict word, arrange the word without meaning order, independent, right? What about the first order, bigram? You can see the bigram and trigram here. The cat sat on the mat near the fireplace and poured softly. You can see here the sentence is somehow a bit, clear and order, but here you can see better but lack long-term coherence. It cannot take coherence. So even the n order, each word may be, has some limitation, but the neural element you can see here where we have the neural element that make prediction, you can see a very full sentence and with good frequency, fluency and other stuff. So this is just to show us one of the key disadvantage of, n-gram language model is that prediction is not coherent and it cannot tackle long-term dependency. Yes, question, Muhammad Adam.
Yes, please. I want to know if there is any relationship between the unigram that each word is independent. Is there a relation between that one and naive Bayes algorithm that assume independency for classes?
Yeah, so I think naive Bayes also, we can say because it does not take care of the order that it depends on that. So maybe we can say that. But that's the idea here. We have, markup chain. So for those people here that are from mathematics, the idea of markup chain, where it's come with this idea of, something actually depend on the previous stuff. So yeah, we can do that with that. This is an example of Google Ngram. So Google actually, they have what we call Google Ngram Viewer, often called Google Ngram. If you click on this one here, we'll be able to see something like this. Let me show us. So if you go here, this is Google Ngram Viewer. So if, for example, if I said good book, can you see this? Good book. Now, how many, the book and good book, they come together, they come together. Good word comes, then book. You can see the percentage, you can see here, there is highest percentage, the books in each year there, But what about if I say book good? Can you see it? Can you see it? It's very minimal to see that. What about if I say book Shamsuddin? There is no bigram because this is bigram, n-gram. So I put two words, bigram. What is the probability of this word occur in each other? What about if I said Shamsuddin, Muslim people? You can see here in those days there is no even bigram word that comes here, but nowadays from this you can see Muslim people is coming. So this is for example, Kano State, Nigeria. This is trigram. So this is trigram. So you can see here there is occurrence of these three words comes together. Kano State, Nigeria. You can see it here and this. What about if I put this here? So you can see Nigeria, Kano State, something like that. What I would say, Nigeria State, Kano. So you can see there is no three words that occur in this, Nigeria State, Kano. There is no any engrams with this word. So this is just, a Google, in those early days that Google comes with this called engram viewer. What is the, probability of words coming, yeah. So they curated this from large book, you can see from books to get these probabilities. So these are some of the limitations of n-gram language models. Number one, n-gram models struggle to capture long-range dependency in natural language. They cannot take care of long dependency. They only look at the previous n word, so no important relationship across sentences are lost. So because they only look at the previous number of words, important relationships are lost. They also lack global coherence and fail on complex syntax. Let's look at an example. So these are the problem of n-gram language model. Number one, they struggle to capture long-range dependency. Number two, they only look at the previous n one. So important relationship across sentences are lost. They lack global coherence because some word or sentence, in beginning of sentence has some linkage with the last sentence in the paragraph. So they lack all this one. So these are the model neural language models. So this one, no other neural language capture long dependency, use deep contextual representation. All these one, they solve this issue. Okay, what is the time? Okay, okay. Okay, let me see how we have. Oh, we have a lot to go. All right, okay. I think we are already there. Let's go there and finish this one. So, how language models are evaluated? So this is a very good question. How language models are evaluated? Now we have seen, a very basic of, n-gram language model where you can be able to predict next word using, the understanding of previous word or only one word or two word. But how do we evaluate language models? So there are two ways to evaluate language model. The quality of language model. So when you create a language model, how do you evaluate its quality? Number two ways. We have extrinsic evaluation. We have intrinsic evaluation. Let's look at them. So what are these two evaluation methods? So extrinsic evaluation, or we sometimes call the in vivo evaluation, best evaluation set model in every real world. So let me just give you an example. Assume now you create a language model for machine translation, or machine translation. For that, or for speech, something. Now, to evaluate this language model, you need to evaluate it in real world scenario. That is what we extrinsic evaluation. Let me say you evaluate a machine translation or speech machine translation. Now you evaluate this model. So to evaluate it, you need to go into the real world, to see when people speak, maybe you develop a text to speech, given a text, you give the speech. Now you create this model and now go to the university or go to market and give people to try for me. You say, okay, you write something and can we hear the model speech? This is real evaluation. You develop several model A, B, C, D. A, B, C, D, for example, 4 models. And now you go to real world and see which one works better. Is this scalable? Can somebody give us an answer? Is this a very scalable approach to evaluate language model in a real world scenario? Is this a scalable approach or good approach? Who can tell us? And what is the disadvantage of this approach? Can anybody tell us? The problem is that we said this is evaluation method. Now you develop your language models for speech and you want to evaluate it. If you want to evaluate, you may not develop only one model, right? You can develop 5 models or 6 or 10. And now these 10 models, you now go to the real world to see which one has a better text to speech or speech to text. For example, when somebody speak and now you see the speech, the text is written, right? So is this a good approach to evaluate language model? Yes. Who is that with this PC?
Yes, sir. Yes, sir. It's Awal. So it's possible, but it may take time to carry out.
Right, good. So I will say this is possible. It may take time. Of course, it has a limitation. Like, it's not scalable. You cannot scale it, on, many languages and many other stuff, right? And it's expensive because you need to go to real, so it's very, very time consuming. This week require full system integration. For example, now you develop speech to text. You develop a model. You need to maybe integrate this speech to text model in your mobile phone or in some tools to go to the people, try to this, had to scale to across many models as well. So, for example, now, you want to develop this model, to evaluate. If you have n number of models, it's very hard. So this is very time consuming. So it's very probable. That is instant. The very, one we do is what we call intrinsic evaluation. Intrinsic evaluation, sometimes we call it perplexity. Yeah, false alternative. So what perplexity does is measure how well a model predict a text. How well a model predict a text, right? So we don't go for intrinsic evaluation, where when we develop the model, we go to real world to evaluate the performance of model. We now go to intrinsic evaluation, where we measure the probability, how well the model predict a set. So if we are talking about how well, because it's probability, so the lower perplexity, the better the model. So the evaluation method for language model, we call it perplexity. So perplexity, when you have a language model and it has a small lower perplexity, then it's a better model because it's a probability. But when we have a very high perplexity, 0.9, 0.8, it means the language model is not good because it's probability. And if the model, so this is basically the idea, perplexity, the formula. If the model assign a higher probability to the full sentence, perplexity is what? Low, right? If the model assign a low probability, perplexity is what? High. So lower perplexity is better model. So this is actually the formula for that. And this is also, just to tell you more about that, lower perplexity means better prediction, higher perplexity means poor prediction. All right, so this is basically, the idea, but there is something here we have, in the formula for perplexity, we have, division. So we have what we call something called also Laplace smoothing, or add-one smoothing. It's a technique used in Ngram language to handle zero probability issue. Because in Ngram, there is zero probability. You may have zero probability. Here, for example, you have 1 divided by 0. You may have zero probability. So in that, we have what we call Laplace smoothing, where we add 1 or something, some numbers, which we call Laplace smoothing, to remove that, issue. All this is that I'm talking about. We're gonna have them in practical class to see them practically how this thing stuff. So what I'm telling us is that this, what we discuss, Ngram language model, bigram, trigram, we'll see them practically in our class. So we have this, if you go to our notebook here, practical, here, when we open this, our Colab, we're gonna see this. So this is, for example, we have, a training corpus here. We have a training corpus. We're gonna do what we call basic tokenization, tokenize a text. As already told you, when we want to do language model, if I have, for example, a word which is boy and boys, right? If you want to do modeling, you need to tokenize, and also do what we call, lemmatization and all other stuff. And the first thing for you to do anything in NLP, you need to do tokenization, to take the sentences and make them into tokens. So this is tokenization. This is unigram model. This is bigram model. This is the probabilities of H1, trigram models. This is text generation, perplexity, how to calculate perplexity, smoothing, add one smoothing. So this is all the practical, for that. And also we have, if you look at it here, we also have assignment for you to do. Exercise, for example, you see that this is exercise to replicate the example we have seen in the example. So now how can we do this? So we're going to have another practical session. The practical session will be led by Lukman, and I don't know. So the idea for this practical session is that when we do our sessions in the morning, in the afternoon, for example, the practical session will be held in the evening. But this week we may not actually hold it in beginning, but maybe within the week. We will communicate when we will have the practical session with you, but you all have this, you can start looking at it. But we will communicate to you the date and time, even if it is, within the week, so that you will have, we will go through with you the practical session of this. So what we discuss all today here for this language model, we'll see them practically. But in the meantime, just go through this notebook. We'll announce, that they will do the practical session, because we cannot do the same practical because we have, exhaust our time, and, yeah. So, any question? Any question?
Yeah, yes, please. Can we have access to these slides that we just used?
Oh, the slide, yeah. So we will upload the slide here. Here is our original previous slide, where we have, if you click here, it will be able to take you to the slide, and you can download the slide, right? So we will upload the slide here for each one. So you can be able to download the slide for yesterday and also the slide for today. Yeah.
Thank you.
And also for more details about what we discussed, because this is just like 1 hour or two, if you want to learn to read more about it, to learn the very good concept, what you need to do is just come here. Let me show you the chapter 3. I may not explain many other things deep, because we have few hours. So as a graduate student, if you are master's PhD student, you need to understand thoroughly. For example, for me, I read this book end to end, cover to cover. Don't be lazy. Don't be lazy. If you want to learn, you want to become good at something, you need to spend good amount of time, because I think there was a book when you say, like, if you want to become good at something, spend like 100 hours on it, learning stuff. So if you want to learn to become good at something, don't just think about something like, spend like 1 hour. No, you need to learn, you need to give time. So this is Ngram language model. If you really interested to learn more, just read this chapter. You'll learn a lot, because we just pick everything from this, book. It's the same book, like, you can see them. It's everything picked from this.
Sorry, sir, you're not sharing your screen, sir.
Oh, okay, sorry. So I come here. I was talking about the slides here. You can see we have the slide for each chapter. For slide, chapter 1, chapter lecture, this slide. But what I said, for each chapter, we have suggested reading for you to understand better. So for you to understand today lecture better, come to here, this book, chapter 3. If you come to this book, chapter 3, you'll be able to, if you don't understand, the only way is to read. There is nothing magic in all this stuff. Just read. Yeah, that's the only thing. Yeah, that is only thing. Just read. So let this thing happen. Now open, and then I will show you. Yeah, so you look at it, language model, right? So this is the Ngram language. This is what we discussed. So if you really want to learn something, as I said, don't read slide. Don't read slide. Yeah, slide is just something we pick. What you need to do, go to the book. That's where you learn the concept. So you can see the Ngram language model. You can see them here. Ngram, you can see it. Markup assumption. This is what we discussed. How to estimate those probabilities. You can see the example I took here. I mentioned here. it is explained more better and you can understand it. Relative frequency, all this stuff, you can see them. You can see it dealing with scale a large language model. You can see them. Evaluated language model, you can see them. Intrinsic evaluation, all this one, evaluated language model, perplexity, you can see it. You can see it, you can see it. Overfitting, we know all this one from machine learning, so we didn't discuss them. Smoothing, interpolation, and backup, Laplace smoothing. So you can see them, right? So what I will urge you is that if you want to really understand this stuff, like not like, university, I know in Nigeria what we made basically just attend the lecture, read the slide, that's all. That's not how to learn. If you really want to learn to become good at what we are doing, you need to spend time reading, make some note, make sure you understand. Our own aim is to guide you, to show you the way, right? To show you the way. This is how things are done, just to show you. And I believe that if you follow our own guide, our suggestion, definitely you'll be able to. In fact, there are some exercises that you can try. Yeah, you can see them. Yeah. So please and please try to do the hard work. We hope at the end of this class, every one of you gonna have his paper. That's one of the good thing for this NLP. We're gonna come with the project. Ideas that everyone will participate to write a paper. We're gonna have also another session for writing in LaTeX because some of you may not know how to write in LaTeX. So we will basically show you the LaTeX, before we start doing. Yeah. Any other question? Yes, Muhammad.
So you mentioned something in your previous class that now the papers in terms of AI, they carry more weight when they were presented and published in conferences than in natural or in like traditional journals. So is there a reason for that?
Right. So what I said here is that in our field AI, NLP, AI in general, unlike maybe like other classical science such as physics, math, they have journals and whatsoever. Now in our field AI and NLP, the best venue is conferences. Why? Because our field is something that is changing every day. Every day things are coming new. In journals, it's something that you can send a paper to journal. It can take a year. Not only this basic journal you send in via university, Jigawa, that you pay like 2,000, 3,000, and you send a journal paper, it take like 1 month. Even the person that will review the journal paper is not expert in the field. It's just like 1 month, 2 months, like 3 weeks to publish. These are not, excellent journal I'm talking about, right? I'm talking about the journals and conferences, not even conferences you attend in Nigeria. Those you attend, for example, you say you attend conference in UK and something like that, all those, small conferences. I'm talking about real ones. So for example, let me show you something. So Google Scholar, computing, computational, let me computational linguistics. Okay. So let me show you here. So in Google Scholar here, look at this one. In Google Scholar, the top venues here, look at the top 20 venues for NLP, which is computational linguistics. Yesterday, I talked about computational linguistics somehow is synonymous with NLP. The very first venue that you will submit a paper to be accepted. In fact, if you apply, for example, for Google, you want to get a job in Google, Microsoft, if you have one paper here in ACL, that is enough for you. In fact, they will write that one of the key requirements is that you must have a paper in either ACL, EMNLP, NACO, TACO, calling, this kind of venues. When you have, for example, here, for NLP, the H index for the best paper, the best stuff is 235, and this is conference. EMNLP is a conference. NACL is a conference. TACO is a journal. TACL is a journal. So when we say here TACO, you can see TACO is a journal. So this is a journal transaction about this journal. So when I'm talking about journal, I'm not even talking about those journals that you go and submit in Nigerian journals, those journals. No, I'm not even talking about them. I'm talking something standard, worldwide, world standard, like, because you will not ever see those journals from Nigeria here. Look at Calling, it's a conference. Look at EACL, it's a conference. Look at LREC, it's a conference. Computer and speech language, I think this one is maybe journal. Yeah, you can see it's a journal, right? So what I'm saying here, from here you can see the top venues are, conferences, right? So one of the key things, the reason why is that, in AI and NLP, things are changing rapidly. Every day they are changing. And there is no need to wait for like 1 year to get if you wait for your 1 year paper to be, from journal to be accepted and published, some other people have already published the paper, similar idea, right? So this is basically one of the reasons for that. So if you are aiming to publish your paper, this will be highly competitive. For example, last year, 2015, some papers submitted to ACL, were 8,000 papers. 8,000 papers worldwide. ACL papers submitted 2025. How many? Look at them. 8,000 papers. Look at them. Over 8,000 papers submission were received in ACL 2025, right? And how many papers were accepted? Only 1,700. So this is to show you this is a very competitive. It's tier 1 conference. Tier 1 conference. But I already told you, if you are just starting, you may not be able to submit to this tier 1 conference because people that are submitting this from top universities around the world, Google, Microsoft, Stanford, everyone are competing. But we also have workshops. So you can aim to submit a workshop. For example, at EACL, or one of these, can you see EACL? EACL. We are organizing a workshop at EACL called Africa NLP 2026. Look at our workshop at EACL. We are organizing this workshop. Look at them. EACL, Africa NLP 2026 workshop. So a workshop paper is even more prestigious in our own field, NLP, than those papers you submit to in Nigerian conferences and journals. So because these are co-located with the main conferences. So look at this, what we're organizing. You can see me here. I'm general chair for this year, African NLP. So this is something that just you may notice. So for each of these conferences that are happening, ACL, EMLP, you will see like 10 workshops co-located, 10 workshops. So if you cannot submit to ACL main conference, you can submit to some of these workshops. So this is, highly competitive. And you can see, like, for example, this year, one of my paper will become a best paper award. Brighter, for example, you can see one of my paper. Yep. So one of my paper become one of the best paper award. Let me go there. A bit of resource. My paper. Brighter motion. Yeah, so you can see here, the space paper I ran, Brighter, Bridging the authored by Shamsuddin and colleague, received Best Resource Paper Award. Can you see that? So one of my paper, this paper received the Best Paper Award at ACL 20 this year, right? This last year, 2025. So this is highly competitive, as we saw, like, there are over 8,000 submissions and, only accept 17%. Like, they accept like, 13 or 14%. All those papers, other they are not submitted, accepted, they are submitted to some time called what we call finding. But I don't know if this answer your question.
So it does. It does. Thank you very much.
Any other question? Any other question? All right. So thank you very much for joining, and please start going through the notebook, and we will let you know when we're gonna have the practical session for today, which will be led by Lukman or by Falalu, two of them. They are our
Hello, sir.
yes, yes.
Yes, sir. It's not a question, rather, it's like I need sort of information. I don't have accessibility to the Discord channel. Can I please have the link again, sir?
Yeah, we shared the link here in the chat. You can join. Yeah, so Lukman, I think we can add Discord channel in our GitHub page. Yeah, in our GitHub page for this, can you add the Discord channel so that people can join?
Okay, sir, I'll do that.
Okay. Any other question? And don't forget to start, don't forget to start going through the Google DeepMind course we already mentioned. You can start the first one, building your own language model. You can go through it, predict. You can see predict the next word, the role of probabilities in language model, probability distribution, n-grams, because this is what we discussed today. Limitation of n-gram, you can see them. Even there is experiment with n-grams. You can see that, right? So yeah, so we expect you to have this course badge by probably in the next 1 week or two. Please do have this. If you finish this one, that will be it. Will take you like just 4 hours to finish this one. You can see that. So please, before next week, try to finish this one. We give you only 1 week to finish it because this is basically cover what we discussed. You can see evaluating a language model. This is what we do today, right? Evaluating language model, which we saw that we have intrinsic and extrinsic language model, right? So this is how to do. You can see we have seen language model. We have seen the n-gram language model. We have seen. So by next week, we expect everyone to submit the certificate for this one course badge. Yeah, we expect you guys to submit that. That will keep you on the loop by participating. Yeah. We will follow up with that with the form to submit this, certificate for this n-gram language model. That's why we told you, we can go hand in hand parallel to make sure that you are learning, getting hands-on stuff. Okay. If there is no question, thank you. More information will be in the Discord. Thank you. And bye-bye.